Good evening, everyone. So we're going to talk about scatterplots and correlation today. So questions to ask of bivariate data. So we're looking at what individuals do the data describe, what are the variables, and specifically how are they measured, right? Or do we have quantitative variables, or do we have categorical variables? And we want to think about, are we trying to explore the nature of the relationship, or do we think that maybe one of the variables explains or even causes changes in the others? So exploring the nature of a relationship is like, do I think these two things might be related in some way, whereas the second part is like, do I think one variable causes the other or explains the other? So this is more of like looking for patterns without suspicion. And this is like if we suspect an association or a causation even. Okay. So bivariate data we have. This is when we're looking at two quantitative variables. So for example, here we have a scatter plot so the x-axis represents years since 1900, so careful here, this really means 1930 and 1945 and so on. And y-axis is the percentage saying that they would vote for a woman president versus the year of the survey. As time increases, we do seem to see that there's an association and more people are willing to vote for a woman president as time increases. So in a scatter plot, the x-axis is called the explanatory variable or the predictor variable. So here we're saying that years is the explanatory variable. So years is my explanatory variable. And then the percent responding yes, I should specify this is years since 1900. And the y-axis, so percent responding yes, is my response variable. Right, so he's doing this one as explanatory, and this as the response. And in this situation, you could very easily flip those two, and it would be fine. So if you're drawing scatterplot, and this, I mean, on the AP test and just life in general, scale, label, my shortcut is title, label, tick mark, second tick mark, title, label, tick, tick. So tick, tick is your scale. If you have tick marks, two tick marks on both axes, then that's scale. And then uniform intervals. So we don't want to see something like this on an interval for the axis where you go 0, 1, 5, 6, right? That would be no. And if you're not beginning at 0, which is acceptable sometimes, then you just want to put that little break there, right? And then you are allowed to, if your data is starting with the hundreds in both x and y, but then goes up by tens, then you could do that, right? Maybe this one goes to 200. Then you go up by tens after that. 110, 120. This one goes to 10, 220. So from there, my scale is consistent. Using breaks can sometimes be a little bit dangerous. You never want to add a break in if you have data in that area, for sure. Even if 0, if 0, 0 is one of your points, do not add a break in your axis. Make the plot large enough. AP gives you plenty of space. And don't compress it into one corner, especially if you're given a whole grid. Okay, so the things you should look for in a scatter plot. Direction, form, strength. So direction is which way are the points going. So we can have points that have a positive direction, a negative direction, or appear to go in no direction. For form, we have what shape do the points make. So we could have linear, quadratic, exponential, logarithmic, any function you can come up with, there can be a form. And then strength is how tightly are the points scattered together. So we can have, this is very weakly correlated. Here we have moderate strength, and then here we have very strong strength in our scatter plot. So putting it all together, so here we have students who took an IQ test, and we want to know if they do better in school. And we took data from 78 7th graders in a rural Midwest school. And again, so direction, form, strength. And we're just going to go ahead and write this out as if we were asked to discuss the scatter plot on an AP-like exam. So there appears to be so my direction is positive. These are generally going up, right? So positive, there's one. Linear, there's two, because these are generally in a straight line, although maybe with some fluctuation here and here, right? So positive linear association between IQ score and GPA. And then I'm missing strength. Really, I should have done strength, direction, form. I'd say it's moderate. It's not, if we didn't have all this cluster, or all of this spread here, and here, and those were more tightly packed together, I would probably say that it's a strong association. But due to those possible outliers towards the end, or towards the low end of IQ score and GPA, we're going to call it a moderate. So moderate positive linear association between IQ score and GPA. And then we also need to add in context. So to say that it's positive and linear, I want to say that as IQ score increases, GPA tends to increase by a constant, because that's also referring to the linearity of it. So, and we'll talk more about regression next class, but you can kind of see that, like, there appears to be this sort of constant increase. As one goes up, the other goes up. Overall, this is a pretty interesting scatter plot because of how strong the association is over here, but then how weak it is as we get closer to the low end. So we do have, in this area, we have some potential outliers. So points that deviate far from the pattern. Particularly this one down there, that has a pretty high IQ, relatively high IQ for that GPA, and this one up over here, who has an IQ at about 70, but a GPA, and I don't know how they're measuring GPA because it goes up to 6 now, but so we have these two very interesting points, we would say. So correlation, and we talked about this. So we only use the word correlation to describe the direction and strength of a linear association. I know it's tempting to use correlation in a lot of other terms, but if it's not linear and it's not bivariate data, then we use the word association. So correlation is strictly to describe the direction and strength of a linear association. And we will use the Pearson's product moment, that ugly, nasty formula. I hope you have it memorized. I'm kidding. You will never have to calculate this by hand. It's on your AP formula chart. It's kind of, so this formula is, remember, this is standard deviation of x, and that's standard deviation of y. So it's kind of like measuring both at the same time and how they go up with each other. I'd be happy to talk more about the math of it later. What you do need to know, so this part's important, is that r is always a number between 0 and 1. If r is greater than 0, then it tells us that there's a positive linear association. So we would have a line with a positive slope. If r is 0, we have no linear association. Now, it does mean no linear association. Here's a great plot where r is going to be 0. You would get r equals 0, but that definitely has a strong association in some other type of way, right? R would be close to 0, right? And if r is negative, then you have a negative slope. Okay. Oh, and then for strength, this is more of a rule of thumb, but if we have r, and this is absolute value of r, so that could mean, so absolute value of r is greater than 0.8. That could also mean that r is lower than negative 0.8. That's negative 0.8, right? So r is greater than positive 0.8 or less than negative 0.8. Same idea for the other two. And these are just rules of thumb. There's no law that says that 0.8 is the cutoff for a strong correlation. That's just kind of the rule of thumb that we follow. So correlation requires both variables to be quantitative, and it has no units. Mathematically, you can actually see that because you're dividing things with units by the same thing, that the units all cancel out. So it has no units. And it is non-resistant to extreme observations or outliers. So what that means is if you have a scatter plot, maybe it's got a really good correlation, and then you add in this point up here, that point is going to affect your R value a lot if you have points that really deviate. And we'll talk about especially what they do to possible regression lines next time. And it doesn't provide a complete description of the data. We're going to look at a really interesting data set, or actually 4 data sets next class that have identical descriptive stats, but don't really look the same. Okay, so R equals 0.4, and again, this very much would still be described as a weak linear association, because it's got a little bit of scatter maybe, or direction going up. R is 0.7. 0.99 is almost exactly a line. If you had R equals 1, then the points would fall exactly on a line. If you had R equals negative 1, then they would also fall exactly on a line, but the line would go down. And this is exactly perfect. If you measured the correlation coefficient of the table for y equals 2x plus 5, you would get R equals 1 exactly. So outliers, when we have bivariate data, we only call a point an outlier if it's an outlier on x and y. So here on the bottom, this is a box plot of just the x values. and this is a box plot of just the y values. So if both box plots show an outlier, then the point overall is an outlier, but you can have points that are outliers on one variable. So like in the IQ GPA graph from a few slides ago, that one didn't have any overall outliers, but it did have several points that were outliers on one axis. But this point overall